Good evening, everyone, and welcome to Soil Health and Amendments with Dr. Schoenau. I'd like to take a moment to recognize that members of the Alberta AgriSystems Living Lab team are grateful to live, work, and be in relation with people from across many traditional territories, covering all regions of Alberta. This acknowledgement is to reaffirm our commitment and our responsibility to improving relationships and our own understanding of local Indigenous people, their cultures, and their knowledge. So I'd like to take a moment to welcome Dr. Schoenau and thank him so much for joining us this evening. Dr. Schoenau is a professor of soil fertility and he's a professional agrologist who works in the Department of Soil Science at the University of Saskatchewan. He holds the Saskatchewan Ministry of Agriculture Soil Nutrient Management Chair in the College of Agriculture and Bioresources and is a fellow of the Agricultural Institute of Canada. Thank you so much for spending your evening with us, Dr. Schoenau.
Great. Thanks, Adrian. It's great to be here and have the opportunity to share a few thoughts and some research results related to some of the work that we've been doing in my research program over the last few years, looking at soil health and amendments, and with the goal to improving the health of prairie soils. So I guess it's always useful to kind of look back in the past, folks, and think about where we've been, where we are, and then maybe to look ahead and see what might be out on the horizon. And I guess when we think back a little bit about cropping systems that were here on the prairies before 1980, for folks, and I realize there's a few maybe weren't around or were pretty young then, but I do remember when cereal-based rotations were dominant, where it was typically wheat or some other type of cereal, and really the rotation there was cereal, and then often followed by a fallow period to try to store some extra moisture, particularly in the drier areas, and using tillage to control weeds. And that type of a system, unfortunately, is one that really was leading to a lot of erosion and degradation of soil quality through wind erosion. And you can remember shown over there on the right-hand side some of the dust storms that we encountered, especially in some of those really dry years like 1988, but also erosion by water, and indeed even tillage erosion, dragging soil from the tops of the hills down into the depressional areas. And so associated with that was a pretty significant reduction in organic matter content compared to what we started out with the native prairie. And I think since that time, though, I think we can give ourselves a little bit of a pat on the back here in Western Canada that we've come a long way. And really moving from a lot of tillage and a monoculture, a single crop type of cropping system towards, and really started in the late 1980s and into the 1990s, the move towards no-till. I guess what some folks, myself included, would really call the no-till revolution, keeping that residue in place, minimal soil disturbance, and really a function of a lot of ingenuity on the part of engineering folks, farmers here in the prairies, and a lot of extension efforts and scientific research to support that type of conservation management system. So I guess in that context, we think how have and how can various management practices, and some of those practices I'm going to talk about certainly involve amendments, improve the health, the productivity, and the fertility of our prairie soils. So we think about what contributes to a healthy soil, and we think about soil health. And back when I was doing a fair bit of work looking at how the no-till system and some of the conservation managements that were coming in back in the late 80s and 90s were coming in, we used a little bit of a different term. We called it soil quality. Which is really very similar to soil health. Perhaps soil health encompasses a little bit more of the biological component of soil compared to what we were dealing with when we were talking about soil quality 20 or 30 years ago. But really, soil health then involves some physical attributes or properties of soil. For example, as shown there in that diagram there, soil compaction or the density of the soil as it relates to ability of roots to penetrate. Also associated with that, a water infiltration or entry, and also the structure of the soil. So we can look at things like aggregate stability. Over on the chemical side, then, things like the pH, which is one of the probably the most commonly measured soil property. We have available nutrients. That falls into my area. I work as soil fertility in particular. And then down in the bottom there, we've got the biological component, which includes things we can measure like mineralizable nitrogen. We can measure the proportion of different fractions of organic matter that are present in the soil that have different resonance times. So we can look at that. We can look at microbial activity, respiration. Indeed, we can look at microbial populations and diversity. But really, I think what's kind of at the center there, as pointed out, is really what's really key, and I think an integral component of all of those is the soil organic matter. And soil organic matter is really the key. And in that context, I was lucky enough to become involved with a project called the Prairie Soil Carbon Balance Project a few years ago, actually led by some folks at Agriculture Canada. Started back in 1996 and continued on. Last sampling that we did was in 2018, looking at soil organic carbon pools as influenced by 21 years of conservation agricultural management practices. And myself, along with my research associate, Dr. Ryan Hangs, and folks from Ag Canada, Brian McConkey and Mervyn St. Luce, did this work. And if people are interested in the details of it, it's actually published now in the Canadian Journal of Soil Science, recent edition, volume 104. But really, in this study that I'm going to talk to you a little bit about, the objective is that I was involved with was to assess soil organic matter forms and functioning in contrasting Saskatchewan soils after 21 years of conservation management practices. So what were we looking at? Well, the kinds of conservation management practices that have been employed and adopted that we were looking at the effect of, no-till, obviously, but also diversification and rotation, particularly where legumes had been brought into the rotation on farms, the elimination of fallow, use of fertilizer and manure at recommended rates. And in the study of soil organic matter, what we typically do is we measure soil carbon. That's what our instruments will measure. We measure by combustion. There's a furnace there that converts the carbon in the organic matter into gas, CO2, that our instrument will measure. And half of soil organic matter is in fact carbon. And so when we talk about soil organic matter levels in the soil changing, really what we're talking about is carbon sequestration. As we increase the organic matter content, we increase invariably the amount of carbon that's stored or contained in that soil in the form of organic matter or humus, as it's sometimes referred to. So in this study, there's actually 90 fields in Saskatchewan across the soil climatic zones, ranging from all the way from the dry brown into the dark brown, black, and gray. And those fields were sampled. These are farm fields that were sampled in 1996. And because they were very carefully marked and located in the field, we're able to go out to those exact same sampling points again in 2018, sample the soils again, and luckily those soils that were sampled in 1996 have been archived, so we could compare directly how those soils had changed over that 21 years. And one of the things that we looked at was the amount of total soil organic carbon. And we looked at this in terms of mass in the 0 to 10 centimeters. That's the top 10 centimeters of the soil. And what we found comparing that mass in that top 10 centimeters, over that 21 years, we did see a significant increase in the carbon that was stored in that top 10 centimeters. When we looked at it on an equivalent mass basis, it was pretty similar, but what we saw was in general, we saw the greatest gains in the organic carbon content in the soils that had the least amounts of carbon to begin with, like the brown and the dark brown soils. And that's kind of typical and explained by the fact that if a soil is fairly low in soil organic matter to begin with, in other words, the pail's pretty empty, it's easier to build up organic carbon in that kind of soil, build organic matter, than in a soil where the pail is pretty well full. And we call this concept carbon saturation. There is a limit to how much organic carbon that you can actually store in a soil, and it's related to the balance of inputs versus outputs. But certainly we're seeing that benefit of altering that balance in conservation management and increasing that soil organic matter content. But particularly related to soil health and properties of the organic matter, which was what we were most interested in my component of the study, we did see this increase in the microbial biomass carbon. In fact, a fairly substantial increase, such that we saw that the microbial biomass carbon sometimes was representing a larger proportion of the organic matter in that soil compared to what existed 21 years ago. And that microbial biomass in that soil, of course, is very important in processes like nutrient turnover of the soil, cycling of nutrients. And so I think seeing both the increase in the soil organic matter content, especially in those soils that were low to begin with, very important from the standpoint of increasing the fertility, because that organic matter is a storehouse of nutrients. The organic matter binds those particles together, so improves the soil structure, and also plays a really important role in increasing water infiltration and also the water holding capacity of the soil. And from a functioning standpoint, that increase in microbial biomass in the content and also the activity that we measured in respiration really points towards an improvement in nutrient turnover, nutrient cycling processes that are important in the functioning of that soil that has been increased by our management systems. So I think that's really a good news story for soil organic matter, soil health, and indeed carbon storage in our prairie soils, folks. But we recognize as well that a lot of those conservation management practices we've been talking about, they're already implemented, they're widespread. So we maybe think a little bit about what are some other things that we can do related to management that may further improve the health and the quality of our soils here. And I guess that thinking about that, well, there's still some soils out there that we would term as marginal soils, kind of heartache soils, where we wonder, well, is there something we could do with those soils that would be better? And I guess one of the things that we think about when it comes to mind when we're thinking about problem soils are those salt-affected soils, saline soils, saline sodic soils. And to that end, thinking about how we might be able to improve those soils and maybe also increase the soil health by increasing the organic matter by taking those salt-affected soils and growing a salt-tolerant forage on them. And maybe coupling that, overlying that with adding some amendments to those soils, which may further help to increase the soil organic matter content and the quality of those soils. So this really leads to a field study that I want to talk a little bit about, conducted by a couple of graduate students over the years, and research associates have been involved with this. And it started in the spring of 2017 with application of amendments and seeding of a salt-tolerant green wheatgrass called AC Saltlander that was actually developed in Dr. Harold Steffun's program at Agriculture Agri-Food Canada at Swift Current in the salt lab. And conducted at some plots in south central Saskatchewan where that kind of typical toe slope or bathtub ring salinity was evident throughout a fair portion of that undulating landscape. So what we did is we set up a series of plots in saline and non-saline portions of a farm field with the seed down of that salt-tolerant grass, overlaying with different amendments that we compared, and those amendments included cattle manure, included leonardite, which is a overburden on coal, which is kind of a precursor to humic materials, and humic material that we included was an application of humic acid in the seed row. And we also, after that, the second application we made over the course of this study, we replaced the humic acid with a char because now the forage was growing and we really didn't have any way to put that humic acid down into the soil. And so what did we find over the course of this study after we seeded it? Well, first off, I have to say that when you seed down a saline area, you have to have some patience. It can take a little while for that grass to get established, and especially with those saline conditions. And shown here in this graph, we have the yield of the wheatgrass, the forage yield in the first year, and our control with no amendment, and then our amendments that we had made that spring, Leonardite at 10 tons per hectare, humic acid at 200 kilograms per hectare placed in the seed row, and then cattle manure that was applied at 10 tons per hectare. I think you can see in that first year, we really didn't see much effect of the amendment there on the yield. And also you can see on that saline soil, a much lower yield of the forage compared to the non-saline. A year later, showing visually this time here, we can see again the saline. It's not as good a growth as what we see in the non-saline, but getting a catch there. And also we had some weeds in there, and certainly very important to try to do something about those weeds. And so we were pretty effective in using a herbicide, fluoxapyr, to do a single application of it to control that kochia weed in those plots, and help reduce the weed competition. And as a result, in year 2, in 2018, we could see the yield of the green wheatgrass. Now we're up to about half of the yield in our saline plots compared to our non-saline plots. And actually, in spring of 2018, we could see a little bit of a positive effect of all of the amendments that we had added there, although that wasn't statistically significant at a 5% level. But some evidence there of maybe having a positive effect there on enhancing the yield in that second year. 2019 was a very dry year. But still, now what we're seeing is actually the yield of that green wheatgrass on the saline site starting now to approach the yield that we were seeing on the non-saline site. In that year, and we're looking at our amendments, we really didn't see any significant effect of the amendments on yield. But as we're moving along, as the years are going on, we're starting to see that green wheatgrass yield on those saline soils catching up to the yields on the non-saline sites. So I guess really what we're seeing is we're getting a palatable forage there, folks, to grow well on a salt-affected land. And that's one of the nice things about the green wheatgrass is it's a fairly palatable forage. And why are we seeing this, finally starting to see this yield catch up to the non-saline site? Is once the roots of that salt-tolerant grass got established in those saline soils, there's shallow groundwater that's actually responsible for the salinity, because when we got water close to the surface, it evaporates and leaves the salts behind. That salt-tolerant grass, the roots could use that shallow groundwater and also the residual nutrients that are in those saline sites that are left behind from years and years of fertilizer application without any crop there growing to take it up and use the nutrients. And actually moving on past 2021 to the last couple of years here, 2022, 2023, those especially, and 2021 as well, those are pretty dry years. And actually, as you can see there in that photo, that grass looks pretty darn good in that saline area of the field. Maybe even a little bit better than the non-saline. And in fact, when we took yields, now we're starting to see in the last couple of years, the yield of that salt-tolerant grass actually exceeding the yield in the saline site, exceeding the yield of what we see in the non-saline site. Again, because we're able to tap into some water and some unused nutrients there that have accumulated in that saline site. Now, we were interested in how that long-term grass seed down may have affected the soil properties after 6 years, 7 years. And so what we did is we did a comparison of the electrical conductivity, which is a measure of salinity, in 2017 versus 2007 in 2023, I should say, compared to 2017 at the start when we first set the experiment up and seeded down the salt tolerant grass. And this is in the top 15 centimeters. And we have to approach this interpretation with caution because we're just looking at a couple of years here. And salinity in the soil does vary a lot from year to year, depending on environmental conditions, wet year versus dry year, how much downward leaching there is, how much the water table's been recharged. But 2023, 2017 are fairly similar years in terms of environmental conditions at the site. And what you can see there, folks, is, well, even in the non-saline, there was a little bit of a decrease in the electrical conductivity associated with the, and salinity associated with that forage seed down. But especially on the right-hand side there, as shown in the saline site that we had, a significant decline in the salinity in that top 15 centimeters, which we may be able to attribute to the roots of that salt-tolerant grass using up the water, lowering that water table, and enabling some downward leaching of the salts out of that surface horizon. So growing that salt-tolerant forage by using soil water and lowering that water table, I think some evidence here that it could help in assisting leaching the salts downward in the profile and reducing the salinity, at least of the soil close to the surface. What about the soil organic matter? This is the soil organic carbon mass change that we saw from samples taken in 2023 after 6 years of forage seed down compared to what we measured in 2017 samples at the start of the study. And there we can see that the soil organic carbon content in that 15 centimeter depth had increased as a result of that seed down. In our control, where we never had any amendments, but we just had the forage seed down, the effects of that over the 6 years, can see an increase, particularly in that saline site. In terms of the effects of the amendments, the addition of the leonardite at 10 tons per hectare, and we also had a treatment there where we had the humic acid initially. We replaced that with the char. We also saw at 10 tons per hectare an increase in the organic carbon content, and also with the manure as well. And in that saline site, it seemed like the char maybe was the one that gave us the greatest organic matter content increase, which probably is a reflection of its recalcitrance or resistance to decomposition. So I think really we're seeing that really growing forages and then adding those carbon containing amendments, particularly at the 10 ton per hectare rate, it was effective in increasing the soil organic carbon, the organic matter, and can contribute then to improved soil health. And really, the roots tell a lot, really provide a very good explanation for what we're seeing there. Looking at the root biomass after 6 years of that salt-tolerant grass compared to adjacent annual cropping system there, we can see there comparing the saltlander, the green wheatgrass seed down to the comparable annual crop there. In this sampling period, it was spring wheat. Looking at the root biomass, 0 to 20, 20 to 40 centimeter, 40 to 60 centimeter depth, you could see the increased root mass and root carbon inputs and water utilization associated with that forage grass. Down at that 40 to 60 centimeter depth there, we do see, comparing saline to non-saline, we do see the root growth is restricted at that depth in the saline sites because it's pretty darn salty down there at that 40 to 60 centimeter depth. I guess another question that we have related to, and this kind of ties into, I think, precision land management and thinking about specific areas of the field where we may have less than optimal soil health, like eroded knolls. Can we improve those areas, improve the productivity through selective addition of amendments? And when we look at those eroded knolls as shown there in that landscape there, which has seen a lot of tillage and has exposed those C horizons or parent material on the tops of the hills, very low in organic matter, often kind of sandy in texture because the clay's been moved out of there, and also quite high pH. is there a way that we can improve the productivity, the health of those areas by adding some amendments that can improve the organic matter, improve the fertility, and improve the productivity of that soil? So we also, in a few years back, embarked on a study to take a look at, can we improve those areas by adding phosphorus fertilizer, micronutrients, manure, alone and in combination, as a kind of site-specific approach to improving the health of the soil at specific locations in the field. And so this project, rebuilding the fertility and productivity of eroded knolls, myself and Dr. Hangs in this work, really dealing with the effects of historical erosion that's occurred in those upper slope knolls. In hummocky fields, we see soils on those knolls, low organic matter, poor fertility, structure. As you can see there, we pull a core of soil out of there. It's not black, it's brown, very thin A horizon below that. You can see the C horizon, the parent material, poor fertility and structure, poor water relations, poor soil health. So I guess the question then that we had in this study, can we address this through different kinds of amendments that are made specifically to those eroded knoll soils? So this is a study that we conducted from 2020 to 2023 to take a look at these amendments on eroded knolls in two south central Saskatchewan fields as influenced by amendment treatments. So what we had as amendments in this study, we had phosphorus fertilizer, monoammonium phosphate, 1152, that we applied at a fairly high rate, about 115 kilograms of P2O5 per hectare, so a fairly high rate of phosphorus, kind of a phosphorus building type strategy. We had zinc that we applied as zinc sulfate, and also zinc that was contained within a char that was actually made from recycled tires that contains a fair bit of zinc. We had copper sulfate, and we had, of course, a manure, a solid cattle manure, and we applied these amendments alone and in combination. Now, our controls that we had, obviously we'd have a control there with no amendment at all, but the other control, what I call the upper level control, was a topsoil replacement treatment. And that's the treatment that you can see there, right there in the center of that photo that Ryan is standing on top. And that was a treatment where we actually went down into the depressional areas of the field, down in there on the left-hand corner, and took a front-end loader and brought that soil out of the depression. And that was soil that had eroded off the tops of that knolls over many years. A lot of it probably back in the 1930s and into the 60s and 70s. Hauled that soil out of the depression and brought it back up and put it on the knoll at a depth of about 10 centimeters. And actually this follows along some work that's being done and has been done in the past by Dr. David Lobb at the University of Manitoba, looking at topsoil replacement as maybe a strategy for increasing the productivity and improving the uniformity of productivity across farm fields that have seen a lot of erosion and redistribution of soil by wind, water, and tillage. So that was our upper level control. And this soil as a starting point was pretty low in phosphorus and zinc. It had moderate copper fertility, low in organic matter, only 1.4% organic carbon. And like a lot of knolls, you could see there, whitish color. We had calcium carbonate, C horizon, parent material exposed, a fairly high pH of about 8.2. And so we made our amendment treatments, and because these areas in the field were pretty large, we were actually able to set up what we call our randomized complete block experimental design with 4 replicates of each treatment. So we had a pretty robust statistical design that we had at our sites. And then we seeded different crops, wheat, peas, and canola on these plots. And we harvested and we measured the grain and the straw yield off of those individual treatment plots. And this is what we found. We made those amendments once in the spring of 2020, and then we followed crop yields over the following 3 years. And this is the wheat yields in the first year. And looking at these graphs here, if you look on the left-hand side, that's our control with nothing added. And then as we move to the right, we've got our different amendments added alone. Monoammonium phosphate, our zinc, our copper alone, and then our different combinations. And finally, over there on the right-hand side, very over, is our topsoil replacement. And as depicted on there, we have our grain yields as open bars, as straw yields as solid bars, and then the striped bars there is the total yield, the grain plus the straw. And that's maybe the easiest to look at and see. So what we can see there in that first year following those amendments, we maybe got a little bit of a yield boost out of the phosphorus. Zinc alone or copper alone, actually we had a little bit of a negative effect of adding copper alone on those eroded knolls without any phosphorus. Follows along from some of our previous work that showed that if you add a lot of copper to a soil without any phosphorus, and it's a phosphorus deficient soil, you can actually have a slight negative yield response, a negative interaction. But looking on the positive side there, in that first year on that wheat, one of the biggest responses that we saw came from our SCM, which stands for solid cattle manure. But our topsoil replacement there, it was the one that tended to be the on top there, so to speak, the king of the hill as far as yield with that spring wheat. Now we also grew peas. Now peas can fix nitrogen, and they also are pretty good scavengers. They actually can grow pretty well on soils that are low in available phosphorus, potassium, zinc, because they're really pretty good scavengers of those nutrients from the soil. And so looking at the pea yields that first year, well, we saw a little bit of a response there, positive response to zinc. And that makes sense because actually pulses are sometimes responsive to zinc fertilization. And we also saw there, I think, really the highest yield there, pretty close to what we saw with our topsoil replacement, where we had zinc and copper and the cattle manure added. But again, the peas are pretty good nutrient scavengers and can do well on some poor soils, can fix their own nitrogen. So really, the topsoil really didn't show up on as the highest yielder with that crop. Now, we also looked at the effect of those amendments on what we call saturated hydraulic conductivity, which is basically a measure or an indication of water infiltration. So we did water infiltration measurements. And there, we thought the cattle manure might have a positive effect, but actually by 2020, a lot of that cattle manure that we'd added in the spring, in fact, had decomposed the straw in there, so wasn't really much different than our control. But that topsoil amendment, it really stood out as having a high water infiltration. So there's some things that the topsoil affects, that topsoil and all of the positive attributes that it has that you really have a hard time duplicating or replacing with individual amendments. Now, 2021 at the site was a severe drought. I don't even want to talk about that one. It was horrible. But in 2022, and this is the third year after amendment, and we see here with the wheat, actually, we can see a positive effect of the phosphorus again. That same negative effect of just having one of the micronutrients alone, like copper. But where we had the zinc and the copper along with the phosphorus in balance, and when we had it with the cattle manure, now we're starting to get some pretty significant yield benefit over our unfertilized, unamended control, and actually pretty close to the topsoil replacement treatment. And interestingly, with canola, showing it in 2023, it was those treatments where we had the balanced availability of the fertilizer nutrients, and also where we had the micronutrients along with the cattle manure that were really the top yielders. And certainly equivalent to it in this case, the mean yields a little bit greater than what we saw with the topsoil replacement. 2023, that was 4 years after we had made our amendment treatment, we did see that topsoil treatment return to king of the hill, as shown there in terms of the yields, and even double the rate of solid cattle manure that we'd added a couple of years before. We still couldn't get ourselves to the same yield that we saw with that topsoil replacement. So the topsoil replacement really has and showed in our study to have the longest lasting effect as a so-called amendment. But really, concluding from this work, we saw some responses to individual nutrients and cattle manure, but we saw those combinations really producing some of the best responses. I think related to having the proper balance, and I think that indicates potential short and longer term benefits from these amendments in restoring the productivity, the health of those eroded knolls, and particularly where you're adding that organic matter as the manure was really of a benefit. Those combinations that provided balanced availability of macros and micros as well. And again, topsoil replacement had the longest lasting effect. It tended to be as maybe things tended to the effects tended to diminish of some of those amendments, but it was where you had that topsoil replacement, all of those good things coming together, including the organic matter, that really seem to be persisting as a benefit to soil health and productivity. The last thing that I want to just talk a little bit about here is, and I've talked about the benefit of solid cattle manure as both a source of organic matter and as a source of available nutrient, particularly over the longer term, but also going back to some of our work related to the effect of liquid manures, in this case, liquid swine manure, where you've got more of that nutrient in that liquid manure in an immediately plant available inorganic form that the plants can use right away. And I would have to say probably some of the biggest responses I've seen in my career of over 35 years of adding things to the soil like fertilizer and other conventional and sometimes kind of weird and wacky amendments to the soil, and looking at crop response. Probably one of the biggest responses I've seen in terms of increased growth of a crop has come from that I've seen has come from some of the work that we did with injected liquid swine manure, and especially on really nutrient deficient old forage stands, old grass stands like that. Injection of liquid swine effluent into an old crested wheat stand in east central Saskatchewan produced some huge yield responses, as I'll show you. And this was liquid manure that was injected in the fall of the year, and you can really see that green up from that manure showing up in the spring. And just putting some numbers on this, in terms of, this was that crested wheat stand, the biomass yield, we were able to see a fourfold increase as shown there in the above ground biomass, the dry mattered yield of that crested wheat from injection of liquid swine manure at 6,600 gallons per acre. And folks, over on the right hand side, a tenfold increase in the seed yield. And so, especially when we're looking at some of these old hayed grass stands, those are some of the soil tests I see with the lowest available nutrient levels, particularly phosphorus and sometimes potassium, sulfur as well. And if it's a grass stand alone, nitrogen's often low in there, and they can be very highly responsive to added nutrient as manure or fertilizer, and especially as shown there with that injected liquid manure. So again, I think if we can think about strategies where we can increase the fertility through amendment addition, increase the organic matter, really then we're looking after our soils and crops, and improving that soil health, that soil quality, means that they can do a better job of looking after us. So with that, Adrian, I will conclude my presentation and thank folks out there. Thank you for the opportunity, Living Labs, to participate. We've got some work going on now with the Living Labs that we've just started, the Central Prairies Living Labs here in Saskatchewan, looking at seed down of legumes into old grass stands to improve the productivity, that hopefully be able to talk about, to have a graduate student working on that with Dr. Bill Belitku from the Crop Development Center, that will be able to have some good information here down the road. So thanks for the opportunity to participate, and happy now to entertain questions, Adrian.
Perfect. Thank you so much, Jeff. We really appreciate it. And we look forward to hearing your results on those Living Labs projects, hopefully in the next year or two.
Yeah.
Everyone, if you have any questions, feel free to pop them in the Q&A or in the chat. And we do have some questions burning a hole in our pocket for you. The first one is, did you just focus on plant matter Within the soil, is there any amendments for future studies to examine the influence of fungus for crops in saline soils?
Yeah, and that's, I think that's a good question, and I think one that certainly makes a person think about a little bit deeper about how some of these amendments, indeed how the forage itself might be influencing the composition of the microbial populations that are in those saline soils, the relative amounts of bacteria versus fungi, for example. That's something we didn't look at in our study, but something that would be useful to look at down the road. I know now in some of our current studies that I'm a collaborator with, where with Dr. Bart Lardner, looking at combinations of different species, legume species, salt tolerant legumes like salt tolerant alfalfa and salt tolerant grasses, green wheatgrass that we've talked about, and also in non-saline soils. Now, as part of the team, have folks like Dr. Bobby Helgeson, who's a soil microbiologist, who's also looking at microbial diversity in those systems. But in that particular study that we set up, which is now going to come to an end in a couple of years, the microbial component, what looking at the actual species composition, wasn't something that we had in there initially, but I think would be interesting to look at. One of the things that we are going to look at in that study that I talked about, the forage seed down into the salt tolerant grasses, next year we're actually going to terminate the stand, and we're going to look at the impact of having those forage grasses in there for 6 or 7 years on the growth of following annual crops,
Very interesting.
canola and wheat.
Perfect. What was the chemical composition of the salt and the calcium in the saline and non-saline
Okay,
sites?
that's a good question. I was actually talking about that project at the Alberta Agronomy Update this morning on a webinar, so it's a little bit fresh in my mind, but not the exact numbers. So in that soil, the electrical conductivity, which is a measure of the salinity, the total salt load, was around 4 to 6 millimoles per centimeter. So it was in that moderately saline range. The soil was not sodic, truly sodic, in that it did not have an SAR, or did not have, I should say, an exchangeable sodium percentage greater than 15%, but there was still a lot of sodium on the exchange complex of those soils, and also a lot of magnesium, but calcium was still the dominant cation on the exchange complex. So, but there was a fairly high load of magnesium, and in particularly a fairly high load of sodium in there as well.
What was the variability in bulk density between the non-saline and saline sites?
Variation in bulk density. So initially, as we started out, there wasn't a whole lot of difference in the surface soil, the 0 to 15 centimeters. In the saline soil, there was a little bit higher bulk density at depth because there was a slight, it wasn't really truly a BNT or a Solonetzik B, according to the strict Canadian system of soil classification, but the B horizon was a little bit denser in the saline site, kind of reflecting that saline sodic nature and the fact that sodium in the soil causes dispersion of soil particles, and leads to that clay alluviation that creates that dense BNT. After we had grown that forage, because of all those roots after 7 years, it did cause a significant decrease in the density of the soil in the surface. So yeah, we were measuring. We also did some water infiltration measurements on those, and I know at the one site, and actually we had a companion site for this at Clavette, south of Saskatoon, another saline soil, and those amendments that we added, the char, the leonardite, and the manure, all increased the infiltration rate compared to the control. So we think of increased water infiltration, that's associated with increased porosity and reduced bulk density.
Interesting. Was there a control of uncultivated soils, or was the baseline the cultivated soil?
Yeah, in this study, the baseline was the cultivated soil. So there was no real native saline or native non-saline that we had in close enough proximity to do that. Although we probably could have. This was done on my farm, and I do have some native prairie out there that I preserved, and there was an area of about a quarter of a mile away that I probably could have used as a native comparable, and it would have been interesting. But we, for the purposes of this and just dealing with spatial variability and some of the side by side comparisons are kind of in terms of being able to consider them valid statistically challenging enough, let alone having something a quarter of a mile away. So
Say
I
that
thought about it, but we didn't actually do the measurements.
perfect. What was the nitrogen and phosphorus equivalence of each of the treatments?
I'm thinking back now. I will say, and I don't recall the exact amounts, but there were higher levels of available nitrate and phosphate in that saline site related to it had had fertilizer applied to it every year since, and I'm going back at rates of about for phosphorus, it was about 30 kilograms of P2O5 per hectare for the last about 20 years. And it's had nitrogen in the cereal and the oil seed at about 50. So those nitrate levels and phosphate levels were elevated in the saline soil compared to the non-saline soil. And I'm thinking that they were probably, by memory, I'm thinking they were about two to three times as high. So there's a lot of residual nutrient that was left in those saline soils because fertilizer had been added, but there'd been very little crop removal. A
Growth.
lot of
Yeah.
weed growth, but what
Yeah.
those weeds do, they take it up and they recycle it. And it had never been, I mean, nobody was cutting that foxtail barley or that kochia for feed. Sometimes it got
Um,
it got just got dissed under.
right. Has any research been done using drainage tile to battle salinity on dry land soils?
Now that sort of gets into another whole area. Uh, I guess people are starting to work with that and look at that, and it can be fairly expensive. I guess I'm more of a fan of the biological approach to it, as opposed to installing the drain. As my feeling is that and listening to what some other work has been done, I've never worked with it myself in my own research, but seeing results of some other research and demonstration and hearing anecdotally out there as well, it seems like it can be successful, but it takes, I think, a couple of things in that you got to have somewhere to drain that water to, and that you need to have enough water moving through that profile through rainfall, that it's going to actually be able to leach that salt downward out of the profile. You get a few dry years like 2021, 2022 in southern Saskatchewan. There wasn't a whole lot of rain, 4 or 5 inches of rain during the growing season. I'd seen some of the installations, and yeah, I mean, you're not having a whole lot of water moving through that profile through those tiles. So I expect the success of it's probably going to be better in wetter areas, and again, where you got somewhere for that water to go.
That makes sense. Was surface residue removed before sampling soil?
Um, in the case of the forage studies that we do, we leave all of that material on the surface of the soil. And even when we are sampling and for research studies and we're taking cores of soil out of there, especially if we're going to do incubations where we measure nutrient release in the sample of soil over time, and we also measure greenhouse gases production in those cores of soil, those intact cores of soil that we take out, we always leave that residue, all of it on the surface, because that's a very, very important part of nutrient recycling. And even if we think of recycling of nutrients like potassium, almost all of the potassium in a crop residue is in a form that can be readily removed by simple water passing through it. And so we want to have that included into it. 50% of the phosphorus and sulfur in a typical crop residue is water soluble, and it will move out of that residue into the mineral soil with water. And so we want to, and then of course we've got it contributing as well through microbial turnover, especially to nitrogen, but other nutrients as well. So we want to have that included in our assessments. So yeah, some people say, well, clean it off, get it out of there. You get a cleaner sample out of there. No, I like to leave it in.
Okay. Any concern with downy brome being a consistent concern with saltlander seed?
Yeah, and I think that, and I've heard that over the years, and I think what happened in the past is that there was some seed that it was that contaminant of the brome had gotten in there, and it really posed an issue. I used seed that actually came from the Agriculture Canada Swift Current. It was high purity seed, and so I never had any issues at all with any type of grassy weeds in there. But I've heard that was that I recall hearing that initially there were some concerns about brome grass being in there and being an introduced species along with the green wheatgrass.
What is the calcium magnesium ratio on both of the sites, both sites?
I would have to go back and calculate that, but the calcium to magnesium ratio was quite a bit higher on the non-saline site compared to the saline site. Again, you're getting that accumulation of the more soluble salts of sulfate in that saline soil, and the more soluble salts of sulfate in order of solubility. Most soluble is your sodium sulfate, which remains in solution. Second is your magnesium sulfate. Your calcium sulfate is the least it's the least soluble, and you can often see in those saline soils when they're dry crystals of gypsum, which is calcium sulfate.
Perfect. What made up the topsoil replacement? What is the source? And I think you answered that you guys went down to the bottom.
Yeah, we went down to the bottom with a front end loader and brought it back up and laid it in the plots at a depth of 10 centimeters.
10 centimeters.
So that
Okay.
was, yeah. And really what that mainly constituted was soil that had been moved from the upslopes down in the depression. So that was soil that was fair bit of that. In fact, I'm pretty sure all of that 10 centimeters was what was on the tops of the hills before. And a question that's commonly asked is did what effect did that removal of that topsoil in that depression have on the productivity down in that depressional area? And we didn't measure that, but I will say that in those areas, you've got a pretty thick A horizon there, and they're actually classified as a humic luvic glycol, such that and some of the modeling work that we had done years ago, and looking at that in terms of validating it in those soils with those really thick A horizons like that, you can take some soil out of there from that, and you can see very little deterioration in productivity. Where you take the soil off, and it really hurts is in those areas where you got a really thin A horizon, and all of a sudden take 10 centimeters off, and whoa, you've lost the A, and now you're down to the B, or maybe even to the C.
Makes sense. What fertilizer rates were used in the Knoll study?
In terms of we made a blanket application, I recall, of about in order to look at the effect of the phosphorus and the micronutrients, and zero out the effect or remove the effect of any differences in nitrogen availability, we had a blanket application, I believe, of 100 kilograms of N per hectare across that knoll. So what we're looking at, and the responses that you saw in that study there, where I showed with the bar graphs there in that eroded knoll study, were really all related back to differences in phosphorus availability, copper and zinc availability, and then maybe also differences, of course, in the organic matter and what it does for soils when you're looking at the effects of the solid cattle manure and the topsoil replacement. Although those two amendments also add nutrient as well.
Did you look at the economics of topsoil replacement versus the addition of amendments?
No, and that wasn't part of our study. But I will say that Dr. David Lobb and Curtis Cavers is a PhD student working with David. That's something that they're more focusing in specifically on that as a particular management treatment.
Perfect. Would you ever equate the negative impacts on crop yields from eroded knolls to the impacts on soils from pipeline construction? And as such, would some of the treatments you used be applicable, as in many cases, the right of ways have subsoil brought to the surface?
Yeah, I think they would have relevance in cases where you had soil disturbance and in the reclamation, those horizons were not replaced properly to duplicate the soil as it originally existed. So you got that parent material up there, that sea horizon. It's kind of similar to those eroded knolls. It's kind of interesting, because the pipeline disturbance. I also hear instances where the some type of an excavation has actually improved the crop growth compared to adjacent areas, and that may have to do with the effects of getting rid of some type of a subsurface layer or horizon that is dense, like a BNT horizon, associated with that disturbance in the installation of some type of a line, a pipe in the ground.
Makes sense. Hi, Jeff. I know you may be looking at statistical significance usually, but have you seen any cases of positive return on investment for amendments like humic acid? I see them being marketed quite often, but I don't see very good data on the ROI or return on investment.
Yeah, and I guess I would say, we did have the humic acid treatment in our study, and we did see that one year that it did seem the year after 2000, it seemed like there was maybe a positive response from it, along with the other amendments. I guess what's sometimes common in some of those studies is that you don't always get statistically significant effects, and they vary from year to year. And it's kind of like adding biologicals as well. There's probably a lot of things that influence the efficacy of some of these amendments, including microbial inoculants that are intended to stimulate plant growth. And when we think of humic materials like humic acid, I guess one of the things that I see in the literature that seems to be most consistent in terms of a positive effect is that they do seem to have some type of a hormonal influence, can stimulate some root growth. And I guess when we think about stimulating root growth, that can be a benefit in some cases, where maybe something's holding back the root growth, or maybe having some increased root growth can be particularly advantageous, such as under a stress condition. But I can also think of a circumstance where if you stimulated root growth, it may actually be a negative, because the plant ends up converting or transferring more of its resources to the roots instead of the above ground material that produces the yield. I think for the rates of application that some humic materials are applied, a few gallons per acre or a few pounds per acre, it seems unlikely that those materials would have a large effect on the properties of the bulk soil, the entire soil volume there, given such a low application rate. But, I guess there is the potential there for a microsite effect, and maybe it could be related to the stimulation of roots. But I think it's kind of like biological products, biofertilizers in general. There's a lot of things out there that will influence the activity of microorganisms, the environmental condition, such that it can be pretty hard to predict, and maybe really kind of hard to expect a consistent positive effect.
Would it be useful to use native prairie soils as a control, since the conditions under which those soils formed are different than the types of mitigation of effects being employed on soils in arable fields? Is it fair to producers to use that as a baseline value, or is it more of a this is where we started scenario?
Yeah, I guess that looks at, sort of where you native prairie, where you started.
Mhm.
And I mean, it's a very much a different system compared to a cultivated cropped field, particularly an annually cropped field. And I guess I would say it might be unrealistic to expect that any type of a management practice like no-till could get you back up to what was in the native prairie. Although
Where
I
you
would
were.
say I would now say never, and on some on-farm studies that we've had where we've actually been able to look at, maybe 40 or 50 years of no-till. There's the odd situation that exists like that, and we've gone on to farm fields. It's quite impressive how that management system can it's getting up closer to what we see in that undisturbed system. But that's a different system. So I guess I would say that using the native prairie as a control, top end control, yeah. But I always like to look at what you started out with and how it changes over time. And I guess we can look at a lot of comparisons where 30 years ago people like say, okay, this is what was in the native prairie, this is how it's changed with 50, 60, 70 years of cultivation. And in majority of cases, and management, it's been a decline. And so then you look at how can you go back up the other way. And also in these studies, not just looking at the soil properties, but also how that relates to the productivity, the yields that are being observed, and even the quality of the crops. Things like the protein content, the content of bioavailable metals in there, like zinc, iron, that are important nutritional constituents, I think is something we also need to be looking at more down the road.
That makes sense. What was the calcium content of the humic treatment?
Huh. That's a good question. I don't know what that was. I guess I think we analyzed the Leonardite. I'm not sure whether we did the commercial humic material or not, but I don't know the answer to that.
Okay. How do those carbon levels compare to undisturbed native prairie soils under native plant communities?
Oh, okay, and they are lower, and I certainly in the non saline site, those levels are lower than what I've measured myself in that native prairie equivalent. So we're talking about, I remember this I do remember, the organic carbon content in the top 15 centimeters of that non-saline site was around 1.5% organic carbon. In that native prairie field I talked about a quarter of a mile away, that I have preserved, albeit ungrazed because I don't have any cattle anymore to graze it. That organic carbon content in there was around 2.8%.
Mm, okay.
So it's lower. But here's the interesting thing is that, the organic carbon concentration in the saline field, or saline portion of the field, the top 15 centimeters compared to the non-saline, they were actually very similar. And I expected the organic carbon, the organic matter content in that saline area to be lower. But I guess maybe it was higher starting out from what was growing there when it was not cultivated at all. And then I also think about foxtail barley and kochia. They're pretty prolific, especially foxtail barley roots
Mhm.
that plant can grow. And I think a kochia, the incredible above ground biomass that it can grow, there's maybe more organic carbon inputs in there and recycling in that saline soil than one
Might think.
perhaps thinks about at the beginning.
No, that makes sense. For the AC Saltlander study, was the cattle manure green or composted?
That cattle manure was composted, and I hate to admit that for uniformity, we actually went with the composted manure that you buy out of a bag. And I'm never really sure whether what you buy, I mean, we try to, is actually really manure and not just something that's kind of scraped up. I mean, this was locally produced and I had a fair degree of confidence in it. I've often in some studies liked to have used a composted manure that came from an actual compost manure pile that I knew, rather than buying it out of a bag. But this was really homogenized, and that was really important to us to have this manure source that was really homogeneous to reduce the variability. That's one of the problems when you start to dig manure out. I know from all the trials that we did out and out of piles, and you don't homogenize it, you end up with a lot of variability from one scoop to another as you're putting it onto your plots.
So then I think you've already answered this for Barry, but can you expand and describe the degree of composting for the cattle manure in both studies? So I think you've covered that.
Yeah,
It came
yeah,
from a
yeah,
bag.
yeah. Yeah. In both, yeah. Let's see. I'm just trying to think of both these. Yeah, no, the topsoil replacement one, that was actual real manure
Mhm.
out of my neighbor's cattle he'd stockpiled.
File.
Yeah. The salinity one, that was manure out of a bag. Yeah.
Okay. Um,
And the stuff was it was passively composted for 1 year in the topsoil replacement study. Yeah.
Perfect. Good memory. If you could redo the study, what would you change or add into the research?
And now which study would that be?
Ian, if you're still on, if you want to type in there which study you're
No, I'm going to see if I can see. Is this in the chat or the question in that?
I think he's putting some answers. This is in the Q&A.
Okay, I'm going to go to
He's
the Q&A. Yeah. Yeah.
popping in some
Oh,
answers.
okay. And
And then
I
he's
see Ian on there. Yeah.
yep. Another question he had for you is where do you see your research going with the advent of CRISPR to upregulate specific genes within our crops?
Yeah. 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 Well, I guess I would want to take a look at how genetic alteration would influence, and being a fertility person, I would say how that relates to nutrient uptake efficiency, and also how that might relate to the efficient use of those nutrients within the plant to produce yield. So yeah, kind of thinking about genetics, especially as they're able to be used to improve the rooting system of crops to increase that nutrient acquisition ability. I think that that's kind of an approach that can help a lot, especially in soils that are already really kind of, I guess you might say, compromised to begin with in terms of their ability to supply nutrients, and improving the ability of crops to use nutrients in uptake nutrients from soils that are less than optimal in their fertility.
What do you think about moving away from monoculture crops as our primary means of growing food?
Yeah, I guess. Well, I would say I'm really quite a fan of diversity, and particularly legumes. I think legumes, their ability to obtain as much as 95% of the nitrogen in the plant from biological nitrogen fixation from the rhizobium nodules in the roots is something that we really want to exploit. And in cases where we're not getting optimal nitrogen fixation, biological nitrogen fixation by the legume, are there ways to improve that? So yeah, I'm thinking that when it comes to when it comes to monoculture versus diversity. I mean, I think of many examples of growing when you grow a legume together with a monocot, the ability of that legume to transfer the nitrogen that's fixed that year to the companion non-legume that year. And what we've seen in others in intercropping trials with annuals, and also with uh, um, alfalfa, brome grass mixtures, 20% transfer or more of nitrogen that's fixed that year to the companion crop. I mean, I think that's really neat. And I think if we could even improve that more, that would be really, really beneficial. And again, it's that kind of synergy, diversity between crops.
Do you have any comments about changes in soil carbon, nitrogen, and phosphorus in cultivated soils when subjected to bale grazing, particularly the area near the bales?
Sure, sure. No, that's a good point because that's something that we've researched in the past. Bale grazing, in-field wintering versus in lot or in-yard feeding. Did work with that with Bart Lardner and Vern Barron in Alberta and others. And really what that work showed is that when you feed cattle in the field compared to feeding them in the yard, feeding them in the field results in much more efficient recycling of the nutrients in the feed, and it was substantial. And that's because in-field feeding reduces the large losses of nutrient that typically occur in the pen, especially the nitrogen gaseous losses. So we were seeing, 30 to 40% recovery of nitrogen in the forage that was present originally in the feed, that was eaten in the animals in the field, compared to single-digit recoveries if it was if it went from the nutrients in the feed that were fed in the yard. What you see related to that when you feed in the field is you do see elevated levels of nutrient in the soil, and we do have to be cognizant, and we also measured that the runoff water from those in-field feeding sites is elevated in nitrogen, particularly, and also phosphorus, especially, so that you do want to retain that runoff water from those in-field feeding sites within that field, rather than allowing it to exit the field and go into some type of a sensitive surface water body.
Makes perfect sense. Um, is a solution to our source of manure using our own feces? So I don't know if you have any comments on using human waste.
Well, yeah, sure, and I mean, I've also worked in the past with sewage sludge, um, and it has its own unique set of issues. Excuse me. Um, Metal content in some areas restricts the application rates of human waste material, such that eventually, because of loading from some of the metals in there, like zinc, maybe nickel or cadmium or whatever, depending on what source it's coming from, because a lot of that human material also gets mixed in with some of the industrial sources. We need to be cognizant of that, and also hearing more about some of the other materials that may be contained in wastewater that ends up as part of municipal sewage, like some detergents, some of those what they call forever chemicals. Also, I think poses some challenges related to the use of human waste, relying on it exclusively as a fertilizer. I think that any type of material like that, it can be applied, but we have to be cognizant of what's in it, and there's probably a limit to how many times and how much we can put on of that kind of material. So again, I think it's looking at combinations of these materials with commercial fertilizers. Monitoring is really important in ensuring that it is a sustainable practice. But I think the bottom line, we got to put back in what we're taking out and harvesting out of the system. And in many cases, exporting right out of our fields, out of our province, out of our country.
Country. Yeah, absolutely, Jeff. One of the projects that we have in our living lab, and we're hoping to have a field day there this year, is using municipal compost and adding municipal compost back to the land. So stay tuned for that.
Yep, yep.
For the eroded knoll study, did you deep cultivate the manure or topsoil treatments to break the surface contact layer between the soil and the amendment?
In an answer, really, no. We tried to keep it minimal disturbance, so that those were actually the amendments were added, and then we basically direct seeded right into the amendments with our seeder. So we didn't want to have a lot of soil disturbance. We also measured in that study runoff. And it's runoff in simulated snowmelt runoff that we actually do by taking an intact slab of soil and then bringing it into the controlled environment, putting snow on, and then collecting the runoff water. And we could see elevated levels of soluble phosphorus in the runoff water, the simulated snowmelt runoff water, in that first year, in that treatment where we had that really high rate of phosphorus that we added as a kind of a soil builder, maybe we didn't get it deep enough into the soil in our applications. So yeah, maybe, there may be some benefits to doing some incorporation, putting things a little bit deeper down into the soil, as was said, maybe and maybe to help mix that material in with the soil, and maybe also to get it down deeper where it isn't as susceptible to loss in runoff.
Perfect. This is a first one for us on a Living Labs webinar, but someone's wondering if you're looking for any MSc students in your program.
Well, I'm getting really close to retirement
Ooh,
with a couple of years, so I'm actually not I'm not taking on the new graduate students anymore.
fair, totally fair. Um, Lots of compliments and
Unfortunately.
yeah,
Because I
and
had a lot of graduate students, and I mean, I will say, and I want to really put a plug in for graduate students, is because they're the folks that really make things happen. They're the folks that make the research go.
Jeff, thank you so much for your excellent presentation and the great answers you gave to all of the questions. Thank you for your time for us tonight, and we look forward to hearing more about your research in the future.
Great, it was lots of fun. Thank you very much, and I hope everybody out there has a good evening. Thank you for attending.
You as well. Thanks, Jeff. Take
You
care.
bet. Yep.
Bye.
Bye bye.